Hi all, I am Agil, Assistant Professor, Postgraduate Department of Chemistry, Majlis Arts and Science College, Puramanur. Today in this section, I would like to discuss about radioactivity. After discussing this section, you will be able to understand what is radioactivity and what are the safety measures that we need to take when we are handling with radioactive materials, applications of radioactivity, and what are the type of radiations that are emitted during radioactive decay. We can start this section by saying the definition of radioactivity. So radioactivity means it's a spontaneous disintegration of atomic nuclei to form a new nuclei by the emission of subatomic particle and electromagnetic energy. So this decay or radioactive emission may have three types. It may alpha radiation, beta radiation, and gamma radiation. It means if a nuclei undergo radioactive decay, it can emit alpha radiation, beta radiation, or gamma radiation. Now we need to discuss all these three type of radiations. So first one, we have alpha radiation. So alpha radiation emission, it consists of emission of alpha particle. Alpha particle means it is similar to helium nuclei. We know helium nuclei means it contains 2 neutrons and 2 protons. So alpha particle emission is equivalent to emission of a helium nuclei. So we have a general example here. I have represented the nuclei as X and atomic number is Z, mass number is A. So when alpha decay, when alpha particle is emitted, that is helium particle is emitted, we are getting a daughter nuclei represented as Y, which has atomic number lesser by 2 unit and mass number lesser by 4 unit. Clear? So also we have another example for alpha particle disintegration, that is uranium 92-238. we are having it undergo alpha particle emission, that is helium nuclei. We are getting new daughter nuclei, that is thorium, having atomic number 90 and mass number 234. So next one is beta radiation. Beta radiation emission consisting of emission of beta particle. Beta particle is similar to electrons, high energy electrons. So when a beta particle is emitted from a nuclei, it is equivalent to emission of electrons. Here also we are having a general example, X, that representing the parent nuclei and it having the atomic number Z and mass number A. When a beta particle is emitted, that is an electron is emitted, the daughter nuclei form, that is Y, which having atomic number greater by 1 unit from the parent nuclei. And the electron that is produced is not from the orbits of the atom, it's from the nucleus and it is formed by the splitting of neutrons. So this is how we could say the beta radiation emission. So next one is the gamma radiation. Gamma radiation, we could say it is simply electromagnetic radiation, just like X-ray, visible light, etc. So when gamma radiation is happening, there is no apparent changes happen to the parent nuclei. Clear? Because it is simply electromagnetic radiation and it having high energy, that means it having high frequency and shorter wavelength. We have discussed about alpha radiation, beta radiation and gamma radiation. These three having different energy, that is alpha radiation that having the lowest energy, beta radiation having energy greater than alpha radiation but less than gamma radiation, and gamma radiation having the highest energy out of these three. Due to this energy difference, their penetrating power is also different. So you could see an image here. So an alpha particle that can be stopped by a thin paper because it having less energy, so that its penetrating power is very low. And the beta particle, it can penetrate through the paper but it can be stopped by an aluminum sheet. This is because the beta particle having higher energy than the alpha particle, so that it can penetrate the paper, but it will be stopped by an aluminum sheet. When we are come to the electromagnetic radiation, that is gamma radiation, it can penetrate the paper and also it can penetrate the aluminum foil, but it will be stopped by a concrete sheet or iron bar. So the gamma radiation is having high penetrating power than alpha and beta. It can penetrate the paper and also the aluminum sheet, and it will be stopped by the concrete sheet. So these radiations, it's very easy to explain, but it is not good for the living organisms. So we have to take much care when we are handling these radioactive elements, because these radiations has lot of problem. When this radiation is come to living organisms, it's make many health issues. So we must be very careful when we are dealing with these radioactive isotopes and these radiations. So we have to take many care when we are handling or doing study with these radioactive elements. So we could say the radioactive materials is not suggestible to use with our bare hand. We can use forceps for handling these radioactive materials, and eating and drinking is not suggestible when we are dealing with these radioactive elements. Then we have to wash our hands after handling these radioactive isotopes, and after usage of these radioactive isotopes, we have to keep them in a lead capsule, and they must be isolated in somewhere. And equipments capable of detecting these radiations must be used to detect the radioactive emission, and we have to take this much of care when we are dealing with this radioactive materials. Now, even though it has lot of problem, we have many uses with this radioactivity and these radioactive isotopes. So we can discuss that. First one is radiometric dating. It means we can use these radioactive isotopes or the radioactivity for determining the age of things that we have. For example, carbon-14 dating. In all living organism, there is C14, carbon-14, that is a radioactive isotope of carbon. So after the death or after the living period, this C14 starts to decay, and by measuring that decay, we could determine the age of that thing, or that's how we are determining the age of fossils. And this is based on the principle that the half-life of the radioactive element, it is independent on the environmental change. That will be constant. It will not be changed with respect to the environmental changes or other things. And the next application is the medical imaging. So you just consider, if we need to make an image of our internal organs or something that is present in our body, we can use medicine which is included with this radioactive isotopes, and this radioactive isotopes that will be absorbed or captured by that organ, and we could use a special camera to image that organ. So we could see the biological things that is happening related to that organ. Next one is tracers. So we can explain this using this example. So here you could see a water pipeline that is going through underground. If we need to find a leakage in that water pipe, we can add tritium containing water through the pipeline. So it will be flow through the pipeline, and using a GM counter or Geiger-Müller counter which can detect the radiation emission. Using that GM counter, we are determining the emission. At some point we are getting more radiation. That means at that point there will be a leakage. Like that, we can use these radioactive isotopes as tracers. Next one is chemotherapy. It's very important. It's done for all cancerous patients. It's for breaking the DNA of the cancerous cell. We could use the high energy gamma radiation. Using that gamma radiation, we can destruct the DNA of cancerous cell. And also it can be used, the gamma radiation can be used to shrink the tumors that present in our body. The next one is the irradiation of produce. That means if we have some food material, if some microorganisms are there present on the food material, we can use the high energy gamma radiation for killing that microorganisms. So these are the main applications or uses of this radioactive isotope or the radioactivity. Now we have the symptoms of radioactive sickness. If someone is affected with this radiation, they will have these symptoms. First one is a loss of body hair, then nausea, fatigue, drop in white blood cells, and sterility after overexposure. So these are the symptoms that happens to a human if he is irradiated with these radiations. So we have discussed about the radioactivity and the problems or relating to the radiations, and we have discussed the different type of radiations, and also we have discussed its applications. Clear? So in this section we have discussed all this. I hope everything is clear. Thank you.